I want you to think about a 6-year-old kid on a Saturday morning. It is 5:30 a.m. The sun has barely come up, and that kid, that absolute menace, is already running laps around the house, bouncing off walls, screaming about dinosaurs, demanding breakfast at full volume. Nobody told them to do that. They just have energy, endless, inexhaustible, frankly annoying energy. Now think about a 45-year-old on that same Saturday morning. 3 coffees, still tired, considering whether getting off the couch is really necessary. Now, here is the question nobody asks. Why? Not why in a lifestyle sense, not sleep hygiene or stress or diet, though those matter too. Why, in a fundamental physics sense, does the universe allow a 6-year-old to have that kind of energy and then slowly, relentlessly take it away? Because it turns out physics has a very precise, very honest, and slightly disturbing answer to that question. And today, we are going to find it. G'day, and welcome back to Curious Physics AU, the channel where we take the universe's most fascinating questions and break them down so clearly anyone can understand them. I am Abdullah, and today we are doing something genuinely unique. We are using physics to answer a question that every single human being on Earth has wondered about at some point in their lives. Why do we run out of energy as we get older? Now, I want to be upfront with you. This video sits at the crossroads of physics, biology, and chemistry. We are going to look at thermodynamics, entropy, quantum mechanics, and the actual energy systems inside your body. Feynman always said the most exciting questions are the ones that sit between the disciplines, the ones where physics and biology meet, where the laws of the universe show up in the most personal, human way possible. This is one of those questions. So grab a cuppa, sit back, and let us figure out why the universe is slowly stealing your energy. Let's go. Before we can talk about losing energy, we need to be precise about what energy actually is. And here's the thing. Most people have a vague, hand-wavy idea of energy. They know it exists. They know they need it. But ask them to define it precisely, and things get murky quickly. Feynman himself said in one of my favorite quotes of his that nobody really knows what energy is. We know what it does. We know how it behaves. But its fundamental nature remains one of physics' deepest mysteries. What we do know is this. Energy is the capacity to do work, to make something happen, to cause change in the universe. And energy comes in many forms. Kinetic energy, the energy of motion, a cricket ball flying through the air, a kid running laps at 5 a.m., potential energy, stored energy, a rock sitting on top of Uluru, a battery sitting in a drawer, thermal energy, the energy of vibrating atoms and molecules, heat, temperature, chemical energy, energy stored in the bonds between atoms, the energy in your food, in petrol, in the oxygen you breathe. And here is the crucial one for today, biochemical energy. The energy your cells use to keep you alive, to power your muscles, your brain, your heartbeat. That biochemical energy has a specific currency in your body. A molecule called ATP, adenosine triphosphate. Think of ATP like Australian dollars. Your body earns them through eating, converting food into ATP, and spends them on everything it does. Moving, thinking, breathing, keeping your heart beating. Every single thing your body does costs ATP. And as we age, the efficiency of that ATP production system changes dramatically. But to understand why, we need to go deeper. We need to talk about the second most important law in all of physics. The second law of thermodynamics. If I had to pick one law of physics that governs everything from the fate of the universe to why your bedroom gets messy, it would be this one. It states, in simple terms, that in any closed system, entropy always increases over time. Now, entropy. That word gets thrown around a lot. Let us define it properly. Entropy is a measure of disorder, of randomness, of the number of possible arrangements a system can be in. Here is the classic Australian analogy. Imagine you have a brand new pack of playing cards, perfectly ordered, ace through king of each suit. That is low entropy, highly organized, one specific arrangement. Now shuffle that deck and shuffle it again and again. The chances of accidentally reshuffling back to perfect order are astronomically small. Almost zero. That is entropy. The universe has an overwhelming statistical preference for disorder over order. Not because disorder is special, but because there are so many more disordered arrangements than ordered ones. Now apply this to your body. Your body is an extraordinarily organized system, cells arranged in precise patterns, proteins folded into exact three-dimensional shapes, DNA coiled and packaged with extraordinary precision, every molecule in exactly the right place, doing exactly the right job. That is incredibly low entropy, spectacularly ordered. And the second law of thermodynamics says the universe will always be pushing against that order, always nudging things towards greater disorder. Your body fights this constantly, every second of every day. Your cells are spending energy to maintain order, to repair damage, to replace worn out molecules, to push back against the relentless thermodynamic tide. When you are young, your body is extraordinarily efficient at this fight. As you age, the efficiency of that fight gradually, inevitably declines. And here is the profound, slightly sobering truth that Feynman would state without flinching: aging, at its most fundamental level, is entropy winning ground. Not all at once, not dramatically, but millimeter by millimeter, disorder creeps in, and your body expends more and more energy just maintaining the fight, and leaving less and less energy for everything else. That tiredness you feel, that is thermodynamics. Now let us zoom in, way in, down to the level of your individual cells. Inside almost every cell in your body, there are tiny structures called mitochondria. You have probably heard them called the powerhouse of the cell, because that is genuinely what they are. Mitochondria are where your body converts the chemical energy from food into ATP, that biochemical currency we talked about earlier. The process they use is called oxidative phosphorylation, and it is one of the most efficient energy conversion processes in all of biology. Here is how it works in simple terms, and this is where it gets beautifully physicsy. Mitochondria maintain a difference in electrical charge across their inner membrane, a voltage, literally a tiny biological battery. Protons, positively charged hydrogen ions, are pumped across the membrane to create this voltage difference. Then, like water flowing through a dam turbine, those protons flow back through a protein called ATP synthase, and that flow, that tiny biological current, drives the synthesis of ATP, energy from electrical potential, converted to chemical energy, ready to power your body. It is, genuinely, an electrical generator inside your cells, billions of them, running continuously every second of your life. Now, here is what happens as you age. Mitochondria have their own DNA, separate from the DNA in your cell nucleus. And that mitochondrial DNA is particularly vulnerable to damage, particularly vulnerable to errors accumulating over time. Every time your mitochondria produce energy, they generate reactive molecules called free radicals as a byproduct. Think of free radicals like exhaust fumes from a car engine, necessary consequence of the process, but damaging to the machinery over time. As decades pass, that damage accumulates in the mitochondrial DNA. The generators become less efficient. They produce less ATP for the same amount of fuel input. Imagine your car engine gradually losing efficiency over years. Same amount of petrol, less power output, more heat generated as waste. That is your aging mitochondria. And fewer efficient mitochondria means less ATP, less biochemical currency, less energy available for everything your body and brain want to do. That afternoon slump you feel at 3 p.m., part of that is mitochondrial efficiency declining with age, physics and biology working together against your afternoon productivity. Now, here is where today's video goes, somewhere most physics channels never take you: quantum biology, because it turns out the energy systems in your body do not just follow classical physics, they use quantum mechanics, the bizarre, counterintuitive rules that govern the behavior of subatomic particles. And Feynman, who spent much of his life working on quantum mechanics, would have absolutely loved this. Here is one example. Photosynthesis, the process plants use to convert sunlight into energy, has been shown to use a quantum phenomenon called quantum coherence. Instead of trying one pathway to convert light energy, like a ball rolling down a single hill, the energy explores multiple pathways simultaneously. Like a quantum particle existing in multiple states at once, it finds the most efficient route through quantum superposition. And it does this at room temperature, in a warm, wet, noisy biological environment which genuinely shocked physicists when it was discovered. Now, researchers believe similar quantum effects may operate in your mitochondria. In the electron transport chain, the process that maintains that biological voltage we talked about, electrons may tunnel through energy barriers rather than going over them. Quantum tunneling inside your cells. As we age and mitochondrial efficiency declines, some researchers believe the quantum coherence of these processes may also be disrupted. The quantum machinery becomes noisier, less precise, less efficient. It is as if the incredibly fine-tuned quantum instruments in your cells gradually go slightly out of tune. We are still in early days of understanding quantum biology, but the emerging picture is extraordinary. Your body is not just a classical machine running on chemistry. It is a quantum machine running on the most fundamental rules of the universe. And like all machines, quantum or classical, it gradually loses its edge over time. Now let us talk about something every student watching this has experienced: mental fatigue. That feeling after 3 hours of studying HSC physics or VCE chemistry where your brain just stops, where reading the same sentence 4 times produces no new understanding whatsoever. Here is the physics of what is actually happening. Your brain is the most energy-hungry organ in your body. It makes up about 2% of your body weight, but consumes roughly 20% of your total energy output. The brain runs almost exclusively on glucose, converted to ATP by, you guessed it, mitochondria in your neurons. Every thought you have, every memory you form, every calculation you do requires the active transport of ions across neuron membranes. Maintaining the electrical potential that allows neurons to fire, that costs ATP, constantly, relentlessly. When your mitochondria are young and efficient, this cost is easily met. Your brain has abundant energy. Thinking is fast, clear, and sustained. As mitochondrial efficiency declines with age, and as the sheer accumulation of cellular maintenance costs increases, your brain gets less of the energy pie. Neural connections that are not frequently used get pruned, partly an energy conservation strategy. The speed of neural transmission, the actual electrical speed of your thoughts, gradually slows. And here is the fascinating physics connection. The ionic pumps in your neurons that maintain electrical potential are themselves subject to the second law. They require constant energy input to maintain order against thermodynamic pressure. Less ATP available means those pumps work harder for less result, means neural signaling becomes less efficient, means thinking requires more conscious effort. That is not weakness. That is thermodynamics. And here is the brilliant part. Exercise, learning, social connection, and good sleep are not just lifestyle advice. They are genuine strategies for maintaining mitochondrial efficiency and slowing the thermodynamic decline. Physics-backed lifestyle advice Feynman would approve. There is one more piece of this puzzle we need to talk about, and it connects physics to biology in a way that is genuinely poetic. Telomeres. At the end of every strand of DNA in your body, there are protective caps called telomeres. Think of them like the plastic tips at the end of a shoelace. They protect the DNA from fraying and damage. Every time a cell divides, copying its DNA, those telomere caps get slightly shorter, like a photocopier that cuts off a tiny bit of the edge of the page each time. When telomeres get too short, the cell can no longer divide safely. It either stops dividing, entering a state called senescence, or it triggers its own death in a process called apoptosis. Now, here is where thermodynamics comes back in. The shortening of telomeres is not random damage. It is a fundamental consequence of the physics of DNA replication. The molecular machinery that copies DNA simply cannot copy all the way to the very end of the strand. It is a geometric and chemical limitation. Every cell division, entropy claims a little more ground, and as more and more cells throughout your body reach their replicative limit, tissue repair slows, organ function gradually declines. The body's ability to maintain its extraordinary organization against thermodynamic pressure and weakens. Energy systems become less efficient. Recovery from exertion takes longer. Sleep, itself an energy-intensive repair process, becomes less restorative. Now, researchers have found something remarkable. Telomere shortening is not entirely fixed. Lifestyle factors, chronic stress, poor sleep, smoking, sedentary behavior accelerate shortening. While exercise, healthy diet, strong social bonds, and mindfulness practices appear to slow it, The enzyme telomerase can actually rebuild telomere length in some cell types, so the thermodynamic clock is real, but it is not entirely beyond our influence. Physics sets the rules, but within those rules, there is more room to move than most people realize. All right, and so now we understand the physics. Let us talk about what you can actually do with this knowledge, because Feynman never just identified a problem, he wanted to understand it well enough to do something about it. Here are the physics-backed strategies for maintaining your energy systems as you age. And yes, the physics genuinely supports each of these. Number one, aerobic exercise. Exercise, particularly sustained aerobic exercise like running, swimming, or cycling, is the single most powerful known stimulus for mitochondrial biogenesis. That is the growth of new mitochondria in your cells. More mitochondria, more efficient energy production, more ATP, more energy. The physics is direct and unambiguous. For Australian students, even a 20-minute run before your study session genuinely improves neural energy availability, not placebo, not motivation, actual mitochondrial output. Number two, quality sleep. Sleep is when your brain runs its glymphatic system, a waste clearance process that flushes out metabolic byproducts accumulated during the day, including damaged proteins and cellular debris. Cutting sleep short is thermodynamically expensive. You are denying your body the repair time it needs to fight entropy. The energy cost compounds across days and weeks. Number three, deliberate cognitive challenge. Learning new things, genuine, effortful learning, stimulates the growth of new neural connections and maintains mitochondrial density in neurons. Your HSC and VCE studies are not just building knowledge, they are maintaining the quantum machinery of your brain. Every hard problem you work through, every concept you genuinely wrestle with, is thermodynamic resistance training. Number four, nutrition as fuel chemistry. Your mitochondria need specific micronutrients to function efficiently. Magnesium, B vitamins, coenzyme Q10, iron. These are not optional extras. They are essential components of the molecular machinery that generates your ATP. The chemistry of your diet directly affects the physics of your energy production. None of these are revolutionary lifestyle tips, but understanding the physics behind them, understanding why they work at the level of thermodynamics and quantum biology, changes how you think about them. They are not just healthy habits, they are physics-informed strategies for slowing entropy. Let us zoom out one final time to the view Feynman would take. The universe began, as far as we understand, in an extraordinarily low entropy state. The Big Bang, perfect order, everything together. Since then, for 13.8 billion years, entropy has been increasing, order diffusing into disorder, energy spreading out, becoming less concentrated, less useful, stars burn, converting concentrated nuclear energy into heat and light spread across the cosmos. Galaxies age, their bright young stars burning out over billions of years, and here on this remarkable pale blue dot, orbiting an ordinary star in an ordinary galaxy, life emerged. Life is the most extraordinary thermodynamic phenomenon in the known universe. It is a pocket of decreasing local entropy, maintained by constantly consuming energy from the environment, pushing back against the tide with breathtaking sophistication. And within life, consciousness emerged, the ability to understand entropy, to comprehend the second law, to look at the universe and ask, why? Your tiredness as you age is the universe reminding you that you are part of this story, that you are made of matter that has been organized into something extraordinarily improbable, something that eats and thinks and wonders and creates. And the energy you feel in your best moments, your clearest thinking, your deepest curiosity, your strongest connections with other people, that energy is the universe experiencing itself through you. Feynman once said, "I would rather have questions that cannot be answered than answers that cannot be questioned." The question of why we age, why we lose energy, sits at the intersection of physics, biology, chemistry, and philosophy. And the answer, incomplete as it still is one of the most beautiful stories physics has ever told. So let us bring it all together. You lose energy as you age because, at the most fundamental level, the second law of thermodynamics is relentless. Entropy increases, order degrades. And the extraordinary biological machinery your body uses to fight that degradation, Your mitochondria, your telomeres, your quantum energy systems gradually becomes less efficient over time. But, and this is the hopeful physics, within those laws, there is genuine room for agency. Exercise, sleep, learning, and nutrition are not just good advice. They are physics informed strategies for keeping your energy systems running as efficiently as possible for as long as possible. You cannot beat entropy. Nobody does. But you can make the fight a beautifully long and energetic one. If this video made you think differently about your own energy, smash that subscribe button and join the Curious Physics AU family. New videos every week, made for Australian students and curious minds everywhere. Drop a comment below. Did the quantum biology section blow your mind? Or was it the mitochondria? Tell me what surprised you most. Share this with a mate, especially one who keeps saying they are too tired to study. Show them the physics. It might just give them the energy to get started. I will catch you in the next one.